guys, welcome to another video. Today's learning objective is to plot and interpret graphs, including reciprocal graphs and exponential graphs. And exponential graphs is for higher tier only. And graphs of non-standard functions in real-life context to find approximate solutions to problems such as kinematic problems involving distance, speed, and acceleration. A bit of a wordy learning objective, but as usual, we'll get into it. Most of this is just going to be working through rote examples to kind of get the hang of this and see the type of questions that come up. So there's not going to be that much theory. So if you do want to, there's kind of 4 rote examples I'm just going to work through. So if you want to skip to any one of those. But yeah, let's get into it. In terms of prerequisite knowledge, kind of, all the graphing stuff we've done so far is really important, especially remembering what reciprocal graphs and exponential graphs kind of look like. But yeah, let's get into it. This is question number 1. So the graph here shows the cost of a journey using a taxi company. Express cabs is shown, The cost of a journey using a different taxi company, fast taxis, is calculated as follows. Total cost equals fixed cost of £3.80 plus £1.40 for every mile that they travelled. Question number 1 is to draw the graph of showing the cost of the journey using the company fast taxis. Okay, so when you see a question like this, right, and you're not too sure what to do or kind of how to plot the graph of fast taxis, what's worthwhile is kind of just thinking of a few values and then just kind of plotting those points and then kind of thinking about what it might look like. So first thing I'm going to do is say if we kind of just make a table and say kind of this is miles and this is total cost, which I'm just going to shorten it to TC because I'm a bit lazy. Miles. So let's say we travel 0 miles. But that seems a bit unrealistic, but kind of just, let's consider it anyways. Let's say you just call up the taxi company, they come here, and then you decide, actually, I don't want to travel. Or you just get in the car and you get straight out. I don't know why you do that, but let's say you do. Well, in that case, you'd still be paying the fixed charge of £3.80, even though you've traveled 0 miles. So the total cost here is £3.80. Okay, let's say you travel 1 mile. Well, in that case, you're going to pay the fixed cost of £3.80 and another £1.40, which is £5.20. And then let's say you travel 2 miles. Well, again, you're going to pay £3.80 plus 2 times 1.4, and that comes out to £6.60, right? And then you can try 3 miles, and then 3 miles is I'll just get my calculator out for this. 3.8 plus, and this. It's 1.4 times by 3 because the distance is 3 miles, right? So 3 times 1.4, and that comes out to £8. Lovely. Okay, and then that can continue so forth, right? And so and now I've got a few values. Let me try plotting this. So I'll zoom in a bit here. Okay, so when it's 0, we're traveling through. It's gonna be 380. So that looks like that's right there. Okay, and then when it was 1, it's 520. So let's go to 1, and we go up to 520, which is right there. And then 2 was 660. So we go to £6. 1, 2, 1, 2, 3. And if you're like me, kind of when you see these lines, your kind of eye just hurt a bit. It's just important, kind of you look away for a second and you come back to it. I've always found that my eyes hurt a bit. But also what you can use is kind of a ruler as well. So you kind of go up to 1, 2, 3, 660, right? And then kind of have a ruler, put it along here, and kind of have a flat ruler along. And then be like, go to 2, which is over here, 660. And then we can try 3, which is 8, which is a bit of an easier one to do. And then you can kind of see this goes in a straight line, right? And so, you just get your ruler out, and you can kind of connect the points, and kind of extend it for the whole range. That's kind of badly drawn, so I've actually got what it's supposed to look like below here. So it wasn't too bad, but yeah, we'll just use this, and I'll rub out the line I've made, so it's just a bit easier for you guys. Okay. So that's fast taxis drawn. And kind of, is there a way of perhaps, instead of plotting these points, just kind of looking at this and then drawing that? Well, kind of there is, right? If you look at this, this actually resembles the equation of a line pretty closely. So look here on the graph. The y-axis is just total cost. So we can just say that, instead of saying total cost, I just call this y, and it's called miles x, right? Well, in that case, we have something like total cost, just we're calling y, 3 plus 3.8 plus 1.4, and distance is x, right? X. And there you go. Now you just got the equation of a straight line, which you can plot pretty easily, right? So a lot of the time, well, the difficulty in the questions is kind of looking at an equation like this, right, which is in kind of these real-world contexts, and turning it into the mathematics you've already seen. But a really good way to do is kind of look at this graph that they've given you, see what's on the y-axis, see what's on the x-axis, and then go to this equation, see what's on, and just kind of turn it into y equals mx plus c, kind of in that form, or at least a form involving x's and y's, which can be a lot easier. Now, the question 2 is write down the fixed charge of express cabs in pounds. Okay, well, how do we convert what the fixed charge is into mathematical notation, right? Well, if we look here, right, for the fast taxis, the fixed charge is 380, and 380 is just the y-intercept from our equation of a straight line. So by the same logic, for express cabs, the y-intercept will be the fixed charge. So we can go down to express cabs, look at the y-intercept, which is 420. So you can write question 2. That was question 1. Question 2 is 4 pounds. And then it says in pounds, so really important to do with the pound sign and the kind of the extra decimal point of 420, not like 4.2. Another way to think about this is for the fixed charge. Well, the fixed charge is when you travel 0 miles, how much will you be charged? So you can do 0, look at 0, and then up here, which is again the y-intercept. Now is the cost per mile, right? Well, again, if we think about what the cost per mile for the fixed for fast taxis was, that was 1.4, right? So for every mile you travel, you pay 1.4 pounds, £1.40. So and that was the gradient, right? Because from our y equals mx plus c, it's right over here, so that's a gradient. So by the same logic, again, we have to find the gradient of express cabs. So kind of, let's just zoom in. Let's pick some nice points. So we know this is 420. Let's pick a nice point, say up here. That's good. So it goes to 9, and then that's 3. So obviously you do this with a ruler. I'm afraid I don't have a ruler on this. So then you can say, you'd say something like the cost per mile is the gradient. So this kind of working is just a bit useful, just to show that, you know, the examiner that we kind of, to talk through a bit about what you're doing in case you kind of mess up this part. So the gradient is change in y over change in x. So I can draw the kind of the thing if I want that rise or run triangle, but gradient is equal to change in y. So useful to write the 2 points that we have. We have 0 and then 4.2, and then we have 3, 9. So change in y is 9 minus 4.2 divided by 3 minus 0, which is 1.6. And then you should put this in words at the end. So you can say, so the cost per mile for express cabs is £1.60. And you can, again, really important to put whenever you do kind of money is to do this to 2 decimal places, because that was something that I always messed up on. I always lost on half for. And then, okay, what would be the cost of a 3-mile journey with express cabs? We're actually kind of lucky we did this by chance. So we go 3, so we look at 3 miles, we go up to the line for express cabs, and that's £9, as you can see. So kind of in this case, what you do is just, you look for, so 3-mile journey is, that's like the x value or whatever the horizontal value should be at 3. So we go to 3, we look at the line for express cabs, and then we just see what the total cost is. Because remember what this line is actually showing in the kind of real world context. It's showing the kind of relationship between the miles that you do and the total cost, as we can tell from this equation here, right? So we just 3 is £9. So you just write question 4. You write the words again, and then I'll just say £9. Again, important, 2 decimal places. Okay. If the cost of a journey is £17 for express tabs, what is the distance travelled? Well, this is just the opposite of what we've just done, right? So we go to cost of 17, and we go along. That's a nice number, and then we just go down. We'll go again with the ruler, and that's £8. So I'm just going to write question 5, 8 miles, not £8, sorry. Again, really important to have this unit here of miles. Okay, if the cost of journey with fast taxis is £45.80, what is the distance travelled? Okay, so now we've got a bit of an issue here, right? Because the graph doesn't go up to the charge of £45.80. So what we could do is, in fact, is just use this equation we have over here. It tells us that the total cost TC is 3.8 plus 1.4, and I'll say for distance, I'll just say, or for miles, I'll put M, or not M because we have that for for the gradient, we'll put D instead, 1.4 D. Okay, we know TC is, what was that? 45.80 is equal to 3.8 plus 1.4 D. Now if we minus 3.8 from both sides, so minus 3.8, minus 3.8, on the right hand side we'll get 1.4D, sorry, 1.4D, and on the left we'll get 45.8 minus 3.8, which 45.8 minus 3.8 is 42. And then if we divide both sides by 1.4, we'll have D is equal to 42 divided by 1.4, which I'm just going to use my calculator in this instance. It's just 30. So then you don't leave it like this, you say therefore like 30 miles, or you say the distance traveled is 30 miles. I'm just not writing it to kind of, so you don't have to watch me write it out. What I did in this case was I didn't write the working of kind of divide both sides by 1.4. You can kind of go from this to this pretty easily if you feel comfortable with what you're doing. If you're not if you want to like have the working written out, feel free to write divide by 1.4, divide by 1.4, for example. Okay, and question 7 is compare the cost of the taxis for the two different companies for journeys up to 9 miles. So look at up to 9 miles, and then we look at express taxis. So express cabs as well. Well, what we can say is that quick thing we can say is that express cabs always cost more than fast taxis for every kind of point along it, as you can see. Because the line of express cabs is above fast taxis, or you can just check every point. Like 4 miles, fast taxis is 9 point something, whereas express cabs is 10 point something. And just kind of use that principle every time. But it's fairly obvious from this that if the express cabs line is above the fast taxis line, then express cabs cost more than fast taxis for every point up to 9 miles. And the other thing you can know is that kind of the gap between them widens. So you can see here that initially the difference is very small, right? So if you're for a small journey, let's say up to a mile, the difference is what? That's what, 5.2. This is 5.8. So it's like 60 pence. But at say 9 miles over here, the difference is what, £1, £2 even. So you can say kind of one thing. So there's kind of 2 observations you can make. So you can say is express cabs always cost more. So I'm just going to say always cost. I'm just going to use the sign greater than. Always cost more than fast taxi. I'd write it out in full. I'm just again just shortening it so it's a bit quicker. And the other thing is you can say like something like for larger distances the difference is greater, or something like that. Larger distances, the difference between the two is larger than for smaller differences. Distances. Sorry, I know this is poor handwriting. I'm just trying to get this done a bit quicker. Okay, so that was kind of one of the way I'd approach one of these questions. Again, so the most important thing is like as soon as you see this is right, the first thing I do straight away is kind of think of the thing on the y as the axis as the kind of thinking of that as y, and think of the whatever's on the horizontal axis as the x. And then look at the equation they've given and convert that into y equals mx plus c, that kind of thing. Or if they haven't given the equation just a line, you just look at it and try to figure out what's happening. And kind of there's like two main things that you need to convert into like real world context. So you have to convert what the y-intercept is saying into a real world context, and what the gradient means in the real world context. So the gradient is saying, in this case, for example, just a kind of quick review. It's saying, remember what the gradient is, right? The gradient is saying how does y change as x changes. So if x increases by 1, how much does y increase by? So this is saying if the distance increases by 1, or the distance traveled increases by 1, how much does total cost increase by? And you can see that's just the cost per mile, right? So that kind of, it's important to be able to convert what the gradient and y-intercept into this real world context. Let's move on to another question that's a bit trickier. So a graph shows the monthly cost of electricity bills for July using the energy company D-ON Energy shown above. The monthly cost of an electric bill using a different energy company, UK Energy, is calculated as follows. The total cost equals monthly charge of £6 plus 0.6 units of energy, which you can see is very similar to the one before. But here, actually, you can see kind of D-ON Energy, right? Actually, the gradient changes. So first, let's think about kind of what each of these things, kind of, as I said before, what the y-intercept means and what the gradient here means. So first thing I kind of, in my head, I'll think, this is the y-axis, this is the x-axis. So the equation of the line, for example, here is saying y is equal to fixed monthly cost, so that's just the 6, plus 0.16x. That's just a quick way. So you can kind of see that's a straight line. But here, let's think about what the y-intercept means. It's saying when 0 units of energy is used, you're still being charged £20. And that's like the fixed tariff, right? The fixed monthly charge. And then the gradient will be, so if kind of the units of energy increases by 1, how much does the total cost increase by? So that's kind of the kind of the cost per unit of energy used, for example. So that's what the gradient is. And you can see for D-ON Energy, for example, that the cost per energy, for every energy or unit used, actually increases beyond 250. And I know it increases because the gradient increases, as I can see. So as soon as you see this, that's something like you should kind of just think through in your head and think about what's the gradient. Is there something interesting going on, for example, like this, where the gradient changes, which translate to what real world thing changing. Okay, so now that I've converted this kind of into the y equals mx plus c equation, I know it's a straight line, and I can just draw that, right, pretty easily. So instead of me kind of mucking up the drawing, I've got the thing here. Let me just rub this out real quick. Okay. We've got, yeah, and also I forgot to mention in this one, right? Make sure you label it, since this was already labeled, but really important to label both of these, and as it's been labeled here. Write down the fixed monthly charge for D-ON Energy in pounds. Again, we've kind of realized that this is the y-intercept, so let's just zoom in. That's £20. So I'll just write that here. 20.00 pounds. Calculate the cost per energy used for D-ON Energy in pounds up to 250 units of energy. Okay, so kind of just pause the video here, try to give this one a go. So remember we said that this was the gradient, so we just have to calculate what the gradient is. Up to two. Remember how it changes? I mentioned it changes at 250, so that's why it says up to 250 units. So let's just pick 2 points. Let's say 250, 35. We've got this one, and 0, 20. So what question is that? That is question 3. So we have the points of, as I said, 250, 35, and 0, 20. So we'd say kind of the units per energy is the gradient or whatever, and calculate the gradient, and just say gradient is equal to change in y, so 35 minus 20, over change in x, which is 250 minus 0, which is 15 over 250, which is 3 over 50, which is 6 over 100, which is 0.06. Okay. Question 4, what would be total monthly cost of with Dion energy if 150 units of energy were used? Okay, so again, what we do is go to 150. The blue line is the one we're interested in. I'll have to zoom in a bit, sorry. And then that's here. So like the one below the thicker line. That's how I always kind of, just to make sure you've done it properly. So there's 5 of these thinner lines, and this is 25, this is 30, so 26, 27, 28, 29. So it's £29. So you just say the total monthly cost is £29 with the wording, obviously, and again, as I said so many times, don't forget the 2 decimal points. If the total monthly cost with UK energy is £30, how many units of energy were used? Again, we can use the graph as we have, or we can actually just use this equation, but a lot of the time it's easier to use the graph, just because it's, if it's within the range, it's already plotted, and you don't have to make, you won't make many errors. You're less likely to make errors, rather. So 30, and we go down to 150. So 150 units of energy. So again, say 150 units of energy. Compare the total monthly cost for energy compare the total monthly cost for the 2 energy companies for different energy usages. Okay, so basically this is just asking, kind of, when it asks you to compare as before the 2 monthly costs, all you have to do is say kind of which one's greater, which one's smaller in this case. So you can say, since Dion energy is above the UK energy line up until, where do they intersect? Okay, is over here. So up until, what is that, 140? Up until 140 units of energy, Dion energy is greater. But then beyond that, up until this next point, UK energy is actually more. So we'd say, we'd say up until 140 units, Dion energy is more expensive than UK. Kind of obviously, again, as I said before, in proper words. And then you can say between 140 and 140 and what point is that? Sorry. That looks like midway between so kind of halfway actually between these two. So that's you kind of say approximately it's halfway, right? And that's what, 295, because there are 5 of these, and so that's 260, 270, 280, 290, and then half again of 10, so 295. So between 140 and 295 units of energy, UK energy is more expensive than Dion. And then after 290, or kind of beyond 295, again we have Dion Dion is more expensive than UK. And if we can see that because kind of UK energy just continues on, and Dion energy is kind of above UK energy. And we kind of have to assume that this line just keeps on going straight up, because we haven't been told that the gradient changes again. And so if this line is steeper than this line, they'll kind of never meet again. And this will always be above that line. As you can kind of tell, right? If there's two lines that meet here, and then just kind of the top line is steeper, it will be increasing quicker than this line. So this line the shallower line will never catch up. The UK energy red line will never catch up with the blue line as long as the gradient doesn't change. And we can assume the gradient doesn't change because we're not told that it does. Okay, let's move on to the next question. Okay, this looks like a distance time graph. And then there's just a bit of theory we need to know for a distance time graph, and kind of the kinematic stuff I mentioned before. I'm not going to go into kind of the reason why this is true. This bit of that'd be a physics lesson, so if you're interested, I'm sure there's a physics video for that. But basically, if we have the gradient of, if we have, say, a distance time graph like this, right? Let's think about what the gradient is. It's saying how does if the time increases by 1 second, for example, how much does distance increase by? Or kind of the gradient in this case is change in distance over change in time. And if you know your physics, that's just speed. So the gradient of a distance time graph is just speed. And if we have, for example, a speed, let's say this was speed instead of distance, well, the gradient in that case would be change in speed over change in time, right? And again, if you know your physics, that's just acceleration. So the gradient of a speed time graph is acceleration. Also, another thing you do need to know is that the area underneath a speed time graph is the distance traveled. So this was speed, this was time, and say it'd be in the first 35 seconds. The area here, when you calculate it, would be the distance journey traveled if this was a speed time graph. So there's three things again. I'll say them one more time. Gradient of a distance time graph is speed. The gradient of a speed time graph is acceleration, and the area underneath the speed time graph is distance. There's just kind of, again, there's some physics behind it and why that works and kind of where that comes from, but I'm not really going to get into it since again, that's more of a physics lesson than the math one. But it's just important to know those things, and those kind of come up sometimes, and important to remember those. So let's do this. Let's do this question now. Okay. The graph above shows two athletes, Jeremy and Harry, competing in a 400-meter race. Jeremy runs at constant speed, calculates average speed correct to 2 decimal places. So again, look, we'd have to know that the gradient is the average speed. So, or we can say, for example, or we can say since with the distance time graph, you tend to start at 0. We don't even have to calculate gradient necessarily. Well, we do have to. What we're doing is calculating gradient, right? But we know it starts at 0, 0, so our life is a bit easier. So we can just pick a nice point, like say 1075, right? And 1075. So gradient is just going to be the gradient is 75 minus 0 over 10 minus 0, which is 75 over 10, which is 7.5. So, and then you say 7.5 in the right units, meters per second. Meters per second. After how many seconds in the race are Jeremy and Harry level? That means that they've covered the same distance. That's what kind of level means. So when did the two lines intersect? When are kind of both Jeremy and Harry at the same distance? That looks like right here. Let's zoom in a bit. Okay, there we are. Which is, what is that? 15, 16, 17, 18, 19, 20. So I just checked that what each of these small lines means is, because there's 5 here, right? 5 of these small lines, and the difference between 20 and 15 is 5. So each of these small lines represents kind of 1 second. So this is just a quick way. 15, 16, and what is it? 15, 16, 17. So that's 17 seconds. So again, for a question, so you can just say 17 seconds. Oops, seconds. Who won the race and by how many seconds? Okay, the question is, we have to remember what the race is. What's a 400-meter race, right? So whoever gets to 400 meters first, i.e. in less time, wins the race, right? So look, this graph actually does go up to 400 meters. Let's see who gets to 400 meters first. Okay, well, we go like this. So the time it takes for Harry to get to 400 meters is, we just go down, is something like over here. So, sorry, actually, let me just kind of redraw that. It was a bit poorly drawn. Please zoom in. Okay. So, because I'm kind of zoomed in, I count, say, it's 1, 2 from this line, right? So I just make sure the line's straight. Okay, what is that, 45, 46, 47? And then we can do the same with, who's that, Jeremy? So where's that, 1, 2 again? So I'm not gonna draw this down just to save us a bit of time. That was the second one, so that's 57. No, sorry, 52. So anyway, 52. So for Jeremy it was 52 seconds. For Harry it was 47 seconds. So Harry wins, and then the difference between those two numbers is 5. So Harry by 5 seconds. How far did Jeremy run after 25 seconds? Give your answer to the nearest 5 meters. This is a bit, we have to watch out for this. Okay, Jeremy after 25 seconds, so 25. Zoom in as well. And then if we, okay. Sorry, I can't really zoom in more, but it looks like that's what it looks like to me. So again, so there's 25, the difference between 270, 175 is 25, and there's 5 lines here, so each like small line represents 5. So this 175, this 180, 185, 190, and that's already to the nearest 5 meters. So 190 meters. What was Harry's speed 20 seconds into the race? So remember, Harry's the one kind of with this changing gradient, right? So that means changing speed, if we remember what gradient stands for. So 20 seconds into the race, we can just find this gradient, kind of the gradient that's through the 20-second bit. So since that, okay, that's kind of an ugly number right there, right? It's somewhere midway, so I'm not actually going to use that number. We can use this point here, which is, what's that, 9? Ooh, come on to it. And 100. And what other point looks nice? Okay, this point looks nice, which is 30. When I say nice, I mean kind of goes through 2 whole numbers, so it's easy to calculate the gradient. And what we have is 180, right? So the points we have are for again, we just have to calculate gradient, and the points we have are was 900, and then 30, 190. So again, gradient is change in y over change in x. So I'll write that here, change in y over change in x. So 190 minus 100 over 30 minus 9, which is 90 over 11, which does not come very nicely. So 90 divided by 11 is, using my calculator, 81.18, and actually kind of recurs that 18 actually recurs. So but remember, it says also to give it to 1 decimal place, so a bit of rounding is needed, just to 8.2. So it's also for speed, right? So we give it in meters per second, and then we can write 1 dB just to specify it again because they mentioned it here. Okay, so that was had to do kind of distance time graphs, and again, really important to remember the three things I said. The gradient of a distance time. I'll actually write this down. Let me get text out. So, gradient of distance time graph, say it with me, is the speed gradient. A bit easier if I just copy this. So the gradient of a speed time graph is what? So again, say it with me, acceleration. And then the area under the line of the speed time graph is the distance. So just kind of three key things that you have to remember. Take a screenshot or whatever if you want to, and just kind of memorize that and burn that into your head, basically. Okay, this is a higher question, kind of all about exponential graphs. I thought it'd be worthwhile to do this anyways, just because it can be these a bit weirder in the sense that there's curves involved and sometimes you can mess that up. But a lot of the time it will be kind of like plot the data as an exponential curve. So you plot the data, which is kind of straightforward enough. It goes, so month is 0, it goes up to here, 8,000, sorry, down here, and then 10,000, and so forth. And once you have those points, kind of important to have a smooth curve. As I mentioned before, it uses kind of the inside of kind of this natural curvature of your wrist. It's quite easy to do that, to use that. It would look pretty bad if I plotted it here, so I'm just going to show you what the answer comes out to. So it comes out to something like this. And then again, this is the same kind of questions that we've seen before, except for there's a bit more leeway in the answers here, because kind of, your curve sometimes isn't as smooth as it could be, and, they're a bit nicer in this case. But use your graph to estimate the ant colony population after 7.5 months. So let's go up to 7.5. I'll have to zoom in again. And then we can see that's just slightly above, I'd say halfway above of the kind of between those two lines. Sorry. So doing my best to draw it halfway above. Okay. Now this is you have numbers like this, 40,000, 35,000. So each one must represent 1,000 each small line. So the next small line above it is 36,000. But between those, so let me zoom in a bit, I'll write 36,000. So this line is 36,000, I'll just write 36. And this is 35, so it's halfway between 36,000 and 35,000. So that's 35,500. So that's what I'd estimate. So 35,500. Again, they're a bit nicer, so sometimes they'll be like, in the answer, they'll be like, you can have an answer between the range of say 36,000 and 35,000, for example. How many months would it take for the ant colony to reach 24,000 ants? Okay, 24,000, that comes out to over here, one below the thick line. So, because it's kind of the answer plot, it's plotted quite nicely for me, so it's a bit easier. But if you do have a bit of leeway, just kind of use your best judgment and be like, again, as I said, the answer usually have a range, so it's kind of, they're not too mean on it. So again, that's 5.5 months, so 5.5 months. And there we are. So I know that was a bit of a longer video, and I worked through a few worked examples. What's important here is just to kind of, with these plotting graphs, just kind of make sure you plot it carefully and nicely. Kind of use a sharp pencil, for example, and then use a nice ruler to draw, especially in the straight lines. Kind of use a nice ruler, or even in this exponential case, you kind of have a nice sharpened pencil, so the line isn't too thick. Sometimes, depending on the kind of your teacher is, they might actually kind of penalize you for saying, oh, the line is too thick, you can't see anything. So it's important to sharpen your pencil before you do this, and kind of just plot these quite nicely. And then when it comes to kind of reading values, don't be like me and kind of make silly mistakes here. Just go over it and check it once or twice. So if you kind of, and also use like a ruler, so say this is 5.5, you get a ruler, so you have a straight edge up to the graph, so it's just easier to read stuff. I mean, I've lost so many marks on kind of these silly mistakes, and kind of I read the wrong value, that kind of stuff. So kind of try avoid those silly mistakes, and you know what I'm going to say next. The only way to avoid silly mistakes is if you practice it so many times that you kind of have a spidey sense of when something's feeling wrong or something. But yeah, hopefully that all made sense, and I'll see you guys in the next video.